the introduction, Brian. I guess before I start, I do have a provocative title, and I was kind of nervous, but after Andrew's talk, I think I'm pretty happy. And other than the fact that he also gave half of my talk, so I feel like I should just stop. But I will answer one question: how AI is important in medical imaging without images, also with images. Okay. So, and also borrowing analogy from Andrew's talk, being an outsider of in healthcare, my primary expertise is in AI. I sort of came in and essentially threw away all the assumptions that have been in place thus far, and wanted to see or ask questions as to what can we do if we sort of attack the problem from scratch, right? So specifically, like the question I started with is, what are the goals of radiology or medical imaging in general? And the US FDA website says that medical imaging refers to several different technologies that are used to view a human body in order to diagnose, monitor, or treat a medical condition. Likewise, NIH website says that radiology is a branch of medicine that uses imaging technology to diagnose and treat disease. So at a high level, the goal here is essentially to treat or diagnose diseases, I guess primarily diagnose the diseases, using some sort of a non-invasive method within a human body, right? And images is basically what we sort of latched onto, because we as humans are very good at visualizing things, as with like everything we just visualize, and it's just easier to understand. And we've come a long way in doing this, right? This is the first ever image of an X-ray acquired in 1895 by this gentleman, and this is what an X-ray looks like right now. So of course a significant difference, and this blob over here actually is not an artifact; it's actually the wedding ring of this person's wife, who was courageous enough to put her hand inside an X-ray machine. And this is what a first MR image of a human chest looked like, which was acquired in '77. And this is what a chest is right now, with a lot of fairly high resolution image and a lot of sort of soft tissue contrast, where you can see quite more detail. And similarly, a couple of other people who are working in the same on similar ideas around the same time, and they acquired their first human finger, which is what it looks like on the left, and this is what a human finger looks like. I mean, there's a controversy here that that them two at the bottom, they got the Nobel Prize for this. However, the Dr. Raymond Damadian did not, but I'll not go into those details. And we've come a long way in fulfilling this goal, not just like in enhancing a specific modality, but we've also explored different modalities that can exist, right? We have excellent technology in X-rays, we have ultrasound, we have CTs, we have MRs, as I just mentioned. And essentially, what I would say is that throughout, what we've done is built these technologies with a goal of generating better and better images, right? And the question I want to ask is, how do we define the term better, right? Does better mean higher image resolution, like from a spatial and volumetric sense? Does better mean an image with a finer detail, like such as soft tissue contrast? Or does better essentially mean that image just should be aesthetically pleasing for the human eye? That is, it should be free of artifacts and stuff like that. Like specifically, this is an interesting point here, because when the fast MRI competition was underway, I've been told. So I mean, I obviously was not a part of it then, but I've been told that when the radiologists actually saw an image which had a little bit of artificial noise injected to it, they thought that that was a much better image than the one that was reconstructed with no noise. So kind of a sort of an interesting, or rather a fairly subjective way of how one defines better, right? Specifically, the question I wanted to ask was, what's the role of a diagnostic information in defining the term better? And actually, can we even quantify this notion of a diagnostic information? Right? And here I would argue that for the most part, most of the work has been done in trying to address the three points that are listed, the first 3 points that are listed in the slide, which is basically a significant amount of effort is made in building both the hardware and the software to generate so-called high-quality images that are aesthetically pleasing. They have very high spatial and volumetric resolution and have extreme fine detail, right? And all of this actually leads to uh, basically a significant complexity in what hardware you're building, as we saw in the previous in the previous set of talks as well. Like consider MRI, for instance. Like this is a typical or what a 0.550 scanner looks like right now from Siemens, and this is what a 70 scanner looks like. It's almost like an airplane, right? So, and why is this the case? And so, just to go a little under the hood, the at a very high level, I would argue that the reason behind this sort of trend of sort of this correlation of generating better images or to which translates to more complex technology is twofold. One is how we collect the data, and the second is what do we collect the data for. Those are the two primary reasons I feel basically drive this direction of complex technology in search of better images. And consider MR again, for instance. Like we know that in MR images we acquire in order to generate an MR image we acquire data in k-space, which is like a complex frequency space measurements. And this process is essentially sequential in nature, that you have to essentially fill in the k-space matrix element-wise. And as you're filling this k-space matrix, you sort of continuously can get better and better signal. And this k-space matrix obviously has a fair bit of structure to it in the sense that the center part holds low frequency, the higher parts hold a higher frequency. And as you fill in this data more and more, the image gets sharper and sharper and so-called better and better, right? And yeah, and so that I feel is basically one of the primary reasons why you need um, complex hardware, because you need large quantities of this k-space data, and you need the high quality of each of the elements of this k-space data, in the sense that the signal to noise ratio should be fairly high, right? So this, as you all know, translates to long scan times using complex hardware. So the question I want to ask is, so assume that all we care about is answering a binary question that whether a specific disease is present or not in a specific individual. Then the question is, do we really want to do this much amount of work? And probably can answer this question easily. And the answer is no, because given this k-space data, now if I start removing the measurements that I had acquired initially, I can still see, still generate an image which is not necessarily of a high quality, in the sense that it has quite a bit of artifacts, which a human eye might find quite disturbing to see. But nevertheless, you can still make out, in this case, intuitively where the pathology exists, specifically in this case, the tumor. Right? And if I keep removing the data, at some point, probably you will hit the limit where probably in addition to the image being completely garbage, you'll start to also miss the pathology. Right? And of course, we know that not all the subsets of the k-space are the same either, right? Like if I randomly eliminate data from within the k-space matrix, then you might get a really bad image with no pathology legible, as opposed to if I do a little bit of more, given a little bit of more thought into it. And the same goes for, like, as I increase my or decrease the quantity of data that I'm acquiring from the k-space, I can still see that you can still infer the pathology, is so long as you are making the right choices as to what lines to acquire. Right? So this tells me something more about it, right? Like it essentially says that probably if I keep stretching this, there must exist some minimal number of k-space measurements in the k-space that are sufficient, or that has sufficient amount of signal to infer whether a specific pathology exists or not, regardless of what the image actually might look like. Right? Or what we call a disease signature, that there must exist a minimal amount of measurements in the space that has enough information to accurately infer whether there is a pathology or not. Right? So the question is, like, can we sort of train a machine learning model or a deep learning model that does two things? One is infer what this disease signature looks like within the k-space. And once you have access to that disease signature, then using the information only from that parts of the k-space, it can actually infer whether a person has that specific pathology or not. Right? And another thing I want to sort of argue is that if we can do such a thing, or if we can build such a system, another sort of conjecture here is that one of the byproducts of the system would be that you may not even need very sort of high quality measurements of these k-space in order for you to just come up with the binary answer. It's not just about the quantity, it's also about the quality, that you might just do away with a very low quality, small amount of measurements and still get the answer, yes or no. And if you can do that, then basically you could use any of the scanners that Tobias and Leo are building currently, or any of the scanners that that Andrew just mentioned, that extremely low field scanners, and just plug in this AI model in there to give you the right answer and as accurately as possible. Right. So, and then of course, like one might argue that that if there are no images, how would one interpret? How would like what will happen to the radiologists and so on and so forth? So the question I'm trying to say is, or the point I'm trying to make here is that you actually absolutely need images, but you need images at the end of the food chain, whereas when you know that a person has, or you have a good suspicion that a person has a specific condition, and then you want to validate that yes, that condition exists and where it is, if that specific pathology. And specifically the case that we the use case that we are working off of is for the problem of early identification of prostate cancer, where I'll go through what the current standard of care is and how can such a technology can potentially change. Okay. So you have patients who are suspected of having a prostate cancer. The current standard of care says that they should undergo a the PSA test, which is like a blood test where they measure the prostate specific antigen within a patient's blood. And if it is below some threshold, the patient is asked to come back after some time. But if it's greater than threshold, then the patient is referred to a full MRI and or probably both, an invasive biopsy as well. Right? And the trouble with this pipeline, of course, is that the PSA test is extremely non-specific. And as a result, what you have is a large number of false positives, and which results in essentially a large number of unnecessary biopsies and also MR scans, which are of course expensive, and biopsies, as we all know, have their own risk. Now, imagine if you have such a technology that we just mentioned, then essentially you could modify this pipeline slightly by having your essentially any patient who has a higher PSA, have that patient undergo through this low field, absolute low field, cheap, accessible scan. And if the scanner says no, then the patient is again put back into the pipeline for a subsequent testing in a after about a year or a 6 month. And only if the scanner says yes, then you put the patient back in. Now, if the accuracy of the scanner is as high as the accuracy of the scanner on the right, except that it's just not generating an image, I would argue that this would really reduce your biopsies and also increase the diagnostic yield of the imaging that the radiologist sees. Right. So which ties back to Andrew's case of when you have such a low field scanner, in this case also equipped with AI, it matters a lot on what the use case would be. And there are plenty of such use cases within healthcare pipeline that these things can be used. So the question is, how can we do this? Recall, so what we want is basically an end-to-end system that does two things. One is detects or infers what we call a disease signature, which is basically a footprint within the case space that has the maximum diagnostic information. And using that information, produce a binary answer. Right? So the question then again, back to my original question, is that how do we define the term best? Right? So recall again that, as I mentioned, that not all the subsets carry the same amount of information, right? So specifically in our case, we define the term best as the subset of the case space that has the largest diagnostic signal. And how we explicitly quantify this is we consider XS as to be the case space for some sampling pattern S, and Y being the clinically relevant variable, in this case, whether the patient has a cancer or not. We define the diagnostic signal as mutual information between the data that exists in XS and your label Y. In this case, again, cancer or no cancer. And then once we have this definition out of our way, and again, there's nice math behind it where you can actually compute the mutual information between Y and, or at least formulate the mutual information between Y and XS, then it's basically a two-step process where you first, in the first step, you train a deep neural network that takes as input some subset of the case space and your Y and estimates your mutual information, what we call a scoring function. And once you have the scoring function at hand, given your case space, you essentially, using some prior distribution based on whatever prior knowledge you have in terms of where the information lies within the case space, you generate a collection of samples and you score each sample, right? And essentially pick the one that has the highest mutual information or which is estimated by step one. And again, I would argue, I would point that this is just one very simplistic way of doing it. Currently, my lab is also working on training the whole thing end to end, in which case you just essentially explicitly identify which parts of the case space might be best for your end answer, and also in an adaptive manner using reinforcement learning type models. But again, that's besides the scope of this talk. But I just wanted to give you an idea that you can actually do this. So, but once you have this sort of the second step complete, then essentially for a given undersampling factor, which you have used to sample these subsets of case space, you essentially pick the subset that has the highest mutual information, right? And once you have that subset, then you then essentially training this model end to end is pretty straightforward. You take as input only the subset of the case space that is identified by a model, and then train another deep learning model to provide you with a yes/no answer. Right? And just to look at sort of some results, that it's actually a fairly hard problem. It's unlike that brain tumor that I showed. The prostate cancer can actually be very subtle. So these are the two images where you actually see or not see, in my case, the cancer that actually exists. And we used sort of our internal, a subset of our internal data set for prostate cancer, and we have fairly large quantities of samples, and it's fairly diverse, both in terms of patients' age distribution, the patient's prostate volume distribution, from the context of lesion sizes, both the height and the width, and from the context of where the lesion lies, whether it is on the left or the right, and peripheral or transitional zone. Okay. So the answer is, can we actually do this, or what would the numbers look like, right? So in this graph, the black line is basically what you can do using a state-of-the-art image-based model where the images are generated using a fully sampled case-based data. So basically, that's the best you can do as far as a deep learning model is concerned, which is about, on the y-axis, I'm showing the area under the curve, and on the x-axis, I have the sampling factor. So of course, like since that's the baseline, that's independent of the sampling factor. And the red line is basically our model where we show that even using 5% of the data, you're not very far away from what the best you can do as far as answer is concerned. And one might argue that once you've learned this case space, why don't you just generate an image and then produce an answer, which is what is conventionally being done in this space. And we tried that as well. And we reconstructed the images using a state-of-the-art reconstruction model and shows that there is a significant, there's a material deterioration in terms of performance as you pick less and less quantities of data. Right? And this phenomena is sort of clearly evident from the actual images that are being generated using this subsample data. Right? On the left, I'm showing the fully sampled case space, the image generated from fully sampled case space data where you can see the tumor somehow. And the rightmost is using only the 8% case space data and using state-of-the-art image reconstruction model. Not necessarily just zero filling the case space, and you can see that at least from a human eye standpoint, the tumor is not at least visible, right? Signal does exist, except that we are not able to capture it. So, and similar results hold essentially in terms of sensitivity and specificity. We also tried the same technique on other problems, specifically for the fast MRI data set, and showed that the results actually generalize for other pathologies and other anatomies. But in general, there are other clinical use cases, as Andrew mentioned, right, where you can use such a technique where it can really change the game in how we actually surveil patients or screen patients and stuff like that. More generally, I'd like to conclude this talk by essentially saying that this is not just specific to prostate cancer. What I'm actually proposing is some sort of a paradigm shift in how people use machine learning in healthcare. Right? The current state of affairs, for the most part, is you assume that you're given an input data, which could be images, which could be case space or whatever. You're either using that to using that input data, you're building a machine learning model either to diagnose a disease or to reconstruct an image and so on and so forth. But most of the effort is placed, as far as the machine learning researcher is concerned, in essentially building this learning model. Right? And what I'm trying to argue is that historically this data set, these images or these case-based stuff, they've always been acquired with the goal of a human eye's interpretation. It had never been acquired with the thought that, okay, some other downstream machine learning model could be used, which need not have an interpretable, which does not require an interpretable input, much like what Andrew mentioned with regards to the signals that you might want to capture and learn from those signals, which may not be human interpretable. Although I'd argue that EKG is, in some sense, is human interpretable because radiology sees it and provides an answer. And so essentially what I'm saying is that break away from this assumption and incorporate your input data as part of your learning mechanism. Let the machine learning model learn what data is necessary. And this data need not be specific to a single modality. You could have all the possible other sensors that could be put into place and have the machine learning model figure out which sensors and what type of signals from each sensors are important for you to make the final diagnosis. Right? And this is much like autonomous cars, right? Why, like when you're building an autonomous car, autonomous driving system that is supposed to aid a human driver, you don't limit or restrict that autonomous car system to only the stereo images, because a human driver can only see stereo images. You use LiDAR information, you use information from infrared sensors, you use information from sonar sensors and stuff like that. And and then build a system that provides the best possible answer. And that's what I think we should do with regards to for medical imaging as well. Or I guess the key takeaway then here is that good things can actually happen if we are willing to break away from this assumption that images are essential, but actually think out of the box and figure out what data is necessary. And that can essentially, you can probably achieve a lot more by probably a lot less data. Finally, many thanks to all my collaborators who are working with me on ideas and essentially pushing these ideas primarily under the leadership of Dan and Harsh, and also my students and research engineers. Thank you.
Thank you, Sumit. Time for one question. You did mention translatability to other anatomies. Like, what's the size of the training data set you think you need to get an accurate model?
So it was the fast MRI plus data set, so which is I think about like a few thousand scans.
Any other questions? If not, let's thank all of our speakers. This closes the session.